In this live of today, we will be reading chapter 3 Atoms and Molecules of class 9 science. This is from NCRT book which is followed in CBSE. Whenever you'll see the video, please share it with your friends so that everybody can take the benefit of it. Let's start with the reading. So here we go with the reading of Atoms and Molecules, chapter 3. The screen is visible to you. Ancient Indian and Greek philosophers have always wondered about the unknown and unseen form of matter. The idea of divisibility of matter was considered long back in India around 500 BC. An Indian philosopher, Maharishi Kannad, postulated that if we go on dividing matter, padarth, we shall get smaller and smaller particles. Ultimately, a stage will come when we shall come across the smallest particles beyond which further division will not be possible. He named these particles as Parmanu. Another Indian philosopher, Pakuda Katyayama, elaborated this doctrine and said that these particles normally exist in a combined form, which gives us various forms of matter. Around the same era, ancient Greek philosophers like Democritus and Leucippus suggested that if we go on dividing matter, a stage will come when particles obtained cannot be divided further. Democritus called these invisible particle atoms, meaning indivisible. All this was based on philosophical considerations, and not much experimental work to validate these ideas could be done till the 18th century. We go ahead reading the next paragraph. By the end of the 18th century, scientists recognized the difference between elements and compounds and naturally became interested in finding out how and why elements combine and what happens when they combine. Antony L. Lavoisier led the foundation of chemical sciences by establishing two important laws of chemical combination. So here we go with the next title, 3.1, Law of Chemical Combination. The following two laws of chemical combination were established after much experimentations by Lavoisier and Joseph L. Proust. 3.1.1, Law of Conservation of Mass. Is there a change in mass when a chemical reaction takes place? Activity 3.1. Take one of the following sets X and Y of chemicals. 1. X copper sulfate, Y sodium carbonate. 2. X barium chloride, Y sodium sulfate. Third, X lead nitrate, Y sodium chloride. Prepare separately a 5% solution of any one pair of substances listed under X and Y, each in 10 ml in water. Take a little amounts of solution of Y in a conical flask and some solution of Y in an ignition tube. Hang the ignition tube in the flask carefully. See that the solutions do not get mixed. Put a cork on the flask. See figure 3.1. So in figure 3.1, which is given here, you can see that here it is written ignition tube containing solution of X dipped in a conical flask containing solution of Y. So let's proceed to the page. So here we go with the reading of second page. Weigh the flask with its content carefully. Now tilt and swirl the flask so that the solution X and Y get mixed. Weigh again. What happens in the reaction flask? Do you think that a chemical reaction has taken place? Why should we pour a cork on the mouth of a flask? Does the mass of the flask and its content change? Law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. 3.1.2. Please do share it with your friends so that everybody can listen to the audio of atoms and molecules. Please hit the like in case you really like the video. So, law of constant proportions. Lavoisier, along with other scientists, noted that many compounds were composed of two or more elements And each such compound had the same elements in the same proportions, irrespective of where the compound came from and who prepared it. In a compound such as water, the ratio of the mass of hydrogen to the mass of oxygen is always 1 is to 8, whatever the source of water. Thus, if 9 gram of water is decomposed, 1 gram of hydrogen and 8 gram of oxygen are always obtained. Similarly, in ammonia, nitrogen and hydrogen are always present in the ratio 14 is to 3 by mass, whatever the method or the source from which it is obtained. Next paragraph. This led to the law of constant proportion, which is also known as the law of definite proportions. This law was stated by Proust as in a chemical substance, the elements are always present in definite proportions by mass. Now we come to the last paragraph. The next problem faced by scientists was to give appropriate explanations of these laws. British chemist John Dalton provided the basic theory about the nature of matter. Dalton picked up the idea of divisibility of matter, which was till then just a philosophy. He took the name atoms as given by the Greeks and said that the smallest particles of matter are atoms. His theory was based on the laws of chemical combination. Dalton's atomic theory provided an explanation for the law of conservation of mass and the law of definite proportions. John Dalton was born in a poor weaver's family in 1766 in England. He began his career as a teacher at the age of 12. 7 years later, he became a school principal. In 1793, Dalton left for Manchester to teach mathematics, physics, and chemistry in a college. He spent most of his life there teaching and researching. In 1808, he presented his atomic theory, which was a turning point in the study of matter. According to Dalton's atomic theory, all matter, whether an element, a compound, or a mixture, is composed of small particles called atoms. The postulates of this theory may be stated as follows. So here we come to the postulates of Dalton's theory. And the first one here is all matter is made up of very tiny particles called atoms, which participate in chemical reactions. Atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. Atoms of a given element are identical in mass and chemical properties. Fourth, atoms of different elements have different masses and chemical properties. Fifth, atoms combine in the ratio of small whole numbers to form compounds. 6. The relative number and kinds of atoms are constant in a given compound. You will study in the next chapter that all the atoms are made up of still smaller particles. Now, the in-text questions that are given. Question number 1. In a reaction, 5.3 gram of sodium carbonate reacted with 6 gram of acetic acid. The products were 2.2 gram of carbon dioxide, zero point 0.9 gram water, and 8.2 gram of sodium acetate. Show that these, we are coming to the next page now. Observations are in agreement with the law of conservation of mass. Sodium carbonate plus acetic acid will give sodium acetate plus carbon dioxide and water. Question number 2. Hydrogen and oxygen combine in the ratio of 1 is to 8 by mass to form water. What mass of oxygen gas would be required to react completely with 3 gram of hydrogen gas? Now, question number 3. Which postulate of Dalton's atomic theory is the result of the law of conservation of mass? Question number 4. Which postulate of Dalton's atomic theory can explain the law of definite proportions? Now we come on to 3.2. What is an atom? Have you ever observed a mason building walls? From these walls, a room and then a collection of rooms to form a building. What is the building block of the huge building? What about the building block of an ant hill? It is a small grain of sand. Similarly, the building blocks of all matters are atoms. How big are atoms? Atoms are very small. They are smaller than anything that we can imagine or compare with. More than millions of atoms, when stacked, would make a layer barely as thick as this sheet of paper. Atomic radius is measured in nanometers. 1 by 10 to the power 9 meter is equals to 1 nanometer. 1 meter is equals to 10 to the power 9 nanometer. So here are relatively sizes are given for few of the things, and their radii is also mentioned in meters. So radii, if it is 10 to the power minus 10 meter, it is seen in atom of hydrogen. Radii 10 to the power minus 9, which is seen in molecule of water. Radii 10 to the power minus 8, molecule of hemoglobin. Radii 10 to the power minus 4 is seen in grain of sand. Radii 10 to the power minus 3 is seen in ant. Radii 10 to the power minus 1 is seen in apple. Now let's come on to this side. We might think that if atoms are so insignificant in size, why should we take care about of them? This is because our entire world is made up of atoms. We may not be able to see them, but they are there and constantly affecting whatever we do. Through modern techniques, we can now produce magnified images of surfaces. Hi, this is just for memes. Hello. Through modern techniques, we can now produce magnified images of surfaces of elements showing the atoms. Figure 3.2, an image of the surface of silicon. What are the modern day symbols of atoms of different elements? Dalton was the first scientist to use the symbols for elements in a very specific sense. When we use a symbol for an element, he also meant a definite quantity of that element, that is, one atom of that element. Berzelius suggested that the symbols of elements may be made from one or two letters of the name of the element. So, figure 3.3 here, symbols for some elements as proposed by Dalton. So you can go through various symbols that are seen here. Hydrogen is seen with circle with a dot in it. Then with the sign of Mercedes seen in phosphorus, circle with C in it for copper, circle with few lines on periphery and G inside is for gold, circle which is colored inside is for carbon, circle with a plus is for sulfur, circle with L written in it is for lead, circle with written in it is for platinas. Blank circle is for oxygen. Circle with I in it is for iron. Circle with S in it is for silver. Circle with few dots on the periphery is for mercury. So similarly, you should know all these. Let's flip on to the next page. And here we go. In the beginning, the names of the elements were derived from the name of the place where they were found for the first time. For example, the name copper was taken from Cyprus. Some names were taken from the specific colors. For example, gold was taken from the English word meaning yellow. Nowadays, IUPAC, International Union of Pure and Applied Chemistry, is an international scientific organization which approves names of elements, symbols, and units. Most of the symbols are the first one or two letters of the element's name in English. The first letter of the symbol is always written as capital letter uppercase and the second letter as a small letter lowercase. I would request the people who are watching this live to please share it with their friends right now. Would be thankful to you. For example, one hydrogen written as capital H, aluminium is written as capital A small l and not capital A capital L. Cobalt is written as capital C small o and not as capital C capital O. Symbol of all these elements are formed from the first letter of the names and a letter appearing later in the name. For examples, 1 chlorine which is written as Cl, zinc written as Zn, etc. Other symbols have been taken from the names of the elements in Latin, German, or Greek. For example, the symbol of iron is Fe from its Latin name ferrum. Sodium is Na from natrium. Potassium is K from kalium. Therefore, each element has a name and a unique chemical symbol. The above table is given for you to refer to what whenever you study about elements. Do not bother to memorize all in one go. With the passage of time and repeated usage, you will automatically be able to reproduce the symbols. Table 3.1 is showing you the symbol of some elements. So aluminium symbol is Al, argon Ar, barium Ba, boron B, boromine Br, calcium Ca, carbon C, chlorine Cl, cobalt Co. Then we come on to the middle part. Copper Cu, fluorine F, gold Au, hydrogen H, iodine I, iron Fe, lead Pb, magnesium Mg, neon Ne. Nitrogen N, oxygen O, potassium K, silicon Si, silver Ag, sodium Na, sulfur S, uranium U, zinc Zn. Let's come on to the next topic, and it is atomic mass. 3.2.2. The most remarkable concept that Dalton's atomic theory proposed was that of the atomic mass. According to him, each element had a characteristic atomic mass. The theory could explain the law of constant proportions so well that scientists were prompted to measure the atomic mass of a atom. Since determining the mass of an individual atom was a relatively difficult task, relative atomic masses were determined using the laws of chemical combinations and the compounds formed. Let us take the example of a compound carbon monoxide written as capital C, capital O formed by carbon and oxygen. It was observed experimentally that 3 gram of carbon combines with 4 gram of oxygen to form CO. In other words, carbon combines with 4 by 3 times its masses of oxygen. Suppose we define the atomic mass unit, earlier abbreviated as AMU, but according to the latest IUPAC recommendation, it is now written as U, unified mass, as equal to the mass of one carbon atom. Then we would assign carbon as atomic mass of 1 U and oxygen an atomic mass of 1.33 U. However, it is more convenient to have these numbers as, we are going to the next page now, whole numbers or as near to a whole numbers as possible. While searching for various atomic mass units, scientists initially took 1 by 16 of the mass of an atom of naturally occurring oxygen as the unit. This was considered relevant due to the two reasons. Oxygen reacted with a large number of elements and formed compounds. This atomic mass unit gave masses of most of the elements as whole numbers. However, in 1961, for a universally accepted atomic mass unit, carbon 12 isotope was chosen as the standard reference for measuring atomic masses. One atomic mass unit is the mass unit exactly equal to exactly 1/12 of the mass of an atom of carbon 12. The relative atomic masses of all the elements have been found with respect to an atom of carbon 12. Imagine a fruit seller selling fruits without any standard weight with him. He takes a watermelon and says that this has the mass equal to 12 units, 12 watermelon units or 12 fruit mass units. He makes 12 equal pieces of the watermelon and finds the mass of each fruit he is selling related to the mass of one piece of the watermelon. Now he sells his fruits by relative fruit mass unit or FMU as in figure 3.4. So figure 3.4 is showing A watermelon, B 12 pieces, C 1 by 12 of watermelon, D how the fruit seller can weigh the fruits using pieces of watermelon. Similarly, the relative atomic mass of the atom of an element is defined as the mass of the atom as compared to 1 by 12 the mass of one carbon 12 atom. Table 3.2, atomic masses of a few elements. So first I'll take the name of the element, and second thing I will be saying the atomic mass in U. Hydrogen 1, carbon 12, nitrogen 14, oxygen 16, sodium 23, magnesium 24, sulfur 32, chlorine 35.5, calcium 40. 3.2.3, how do atoms exist? Atoms of most elements are not able to exist independently. Atoms form molecules and ions. These molecules or ions aggregate in large numbers to form the matter that we can see, feel, or touch. Now, let's come to the in-text questions. Define the atomic mass unit. Why is it not possible to see an atom with naked eyes? Next topic. 3.3, what is a molecule? A molecule is in general a group of two or more atoms that are chemically bonded together, that is, tightly held together by attractive forces. A molecule can be defined as the smallest particle of an element or a compound that is capable of an independent existence and shows all the properties of that substance. Atoms of the same element or of different elements can join together to form molecules. Now let's come on to the next page. So here we go with 3.3.1 molecules of elements. The molecules of an element are constituted by the same type of atoms. Molecules of many elements such as argon, Ar, helium, He, etc. are made up of only one atom of that element. But this is not the case with most of the nonmetals. For example, a molecule of oxygen consists of two atoms of oxygen and hence it is known as diatomic molecule O2. If three atoms of oxygen unite into a two molecule instead of the unusual two, we get ozone, which is written as O3. The number of atoms constituting a molecule is known as its atomicity. Metals and some other elements such as carbon do not have a simple structure but consist of a very large and indefinite number of atoms bonded together. Let us look at the atomicity of some of the nonmetals. So table 3.3 is showing the atomicity of some of the elements. First, I will be taking the type of the element, then I will be saying the name and then the atomicity. So I'll be seeing all the nonmetals: argon monoatomic, helium monoatomic, oxygen diatomic, hydrogen diatomic, nitrogen diatomic, chlorine diatomic, phosphorus tetraatomic, sulfur polyatomic. 3.3.2 Molecules of compounds. Atoms of different elements join together in definite proportions to form molecules of compounds. Few examples are given in table 3.4. So here is our table 3.4, molecules of some compounds. So compound is water, written as H2O. Combining elements are hydrogen and oxygen, and the ratio by mass is 1:8. Next compound is ammonia, written as NH3. Combining elements are nitrogen and hydrogen, and ratio by mass is 14:3. Next compound is carbon dioxide. Combining elements are carbon and oxygen, and ratio by mass is 3:8. Activity 3.2. Refer to table 3.4 for ratio by mass of atoms present in molecules and table 3.2. For atomic masses of elements, find the ratio of by number of the atoms of elements in the molecules of compounds given in table 3.4. The ratio by number of atoms for a water molecule can be found as follows. So element is H, ratio by mass is 1, atomic mass is U1, mass ratio divided by atomic mass is 1:1, that will give you 1, and simplest ratio is 2. Element is oxygen, ratio by mass is 8, atomic mass in U is 16, mass ratio is 2, atomic mass is 8 by 16, means 1 by 2, and simplest ratio is 1. Thus the ratio by number of atoms for water is H is to O is equals to 2:1. Let's come on to the next paragraph 3.3.3. What is an ion? Compounds composed of metals and nonmetals contain charged species. The charged species are known as ions, and ions may consist of a single charged atom or a group of atoms that have a net charge on them. An ion can be negatively or positively charged. A negatively charged ion is called an anion, and the positively charged ion is known as a cation. Take, for example, sodium chloride NaCl. Its constituent particles are positively charged sodium ions Na plus and negatively charged. Coming on to the next page. Here we go. Chloride ions or Cl minus. A group of atoms carrying a charge is known as polyatomic ion. Table 3.6. We shall learn more about the formation of ions in chapter 4. Table 3.5. Some ionic compounds. Ionic compound is calcium oxide. Constituting elements are calcium and oxygen, combining in the ratio 5:2. Ionic compound next is magnesium sulfide. Constituting elements are magnesium and sulfur, and ratio by mass is 3:4. Ionic compound is sodium chloride. Constituting elements are sodium and chlorine, and ratio by mass is 23:35.5. Next heading, writing chemical formula. The chemical formula of a compound is a symbolic representation of its composition. The chemical formula of different compounds can be written easily. For this exercise, we need to learn the symbols and combining capacity of the elements. The combining power or capacity of an element is known as its valency. Valency can be used to find out how the atoms of an element will combine with the atom of the another element to form chemical compound. The valency of the atom of an element can be thought of as hands or arms of that atom. Human beings have two arms and octopus has eight. If one octopus has to catch hold of a few people in such a manner that all eight arms of the octopus and both arms of all the humans are locked, how many humans do you think the octopus can hold? Represent the octopus with O and humans with H. Can you write a formula for this combination? Do you get OH4 as the formula? The subscript 4 indicates the number of human held by octopus. The valencies of some common ions are given in table 3.6. We will learn more about valency in the next chapter. So here is the table 3.6 that will tell you the names and symbols of some ions. So valency 1 is shown by sodium, potassium, silver, copper 1. They all are written with a plus on it as a superscript. Hi, Mastermind. Thank you for joining. Valency 2 is exhibited by magnesium, calcium, zinc, iron 2, copper 2, and they all are written with a superscript 2 plus. Valency 3, aluminium, iron 3, and it is shown by these two only, and that is why they are written with the superscript 3 plus. Non-metallic elements, hydrogen can exist as H plus, hydride as H minus, chloride as Cl minus, bromide as Br minus, iodide as I minus, oxide as O2 minus, sulfide as S2 minus, nitride as N3 minus. Polyatomic ions are these ones. Ammonium written as NH4 plus, hydroxide OH minus, nitrate NO3 minus, hydrogen carbonate HCO3 minus, carbonate CO32 minus, sulfite SO32 minus, sulfate SO42 minus, phosphate PO43 minus. So some elements show more than one valency. Roman numeral shows their valency in a bracket. Now we move on to the next page. Here we go. The rules that you have to follow while writing a chemical formula are as follows. The valencies or charges on the ion must balance. When a compound consists of a metal and a non-metal, the name or symbol of the metal is written first. For example, calcium oxide CaO, sodium chloride NaCl, iron sulfide FeS, copper oxide CuO, etc., where oxygen, chlorine, sulfur are non-metals and are written on the right, whereas calcium, sodium, iron, and copper are metals and are written on the left. In compounds formed by polyatomic ions, the number of ions present in the compound is indicated by enclosing the formula of ion in a bracket and writing the number of ions outside the bracket. For example, MgOH whole 2. In case the number of polyatomic ion is 1, the bracket is not required and it will be written as, for example, NaOH. Let's come on to the next part. This is 3.4.1 formula of simple compounds. The simple compounds which are made up of two different elements are called binary compounds. Valencies of some ions are given in table 3.6. You can use these to write formula for compounds. While writing the chemical formula for compounds, we write the constituent elements and their valencies as shown below. Then we must cross over the valencies of the combining atoms. Mastermind, thank you for joining here. This video is specifically the audio of atoms and molecules. I'll record a video in it and let you know. Meanwhile, the students who have joined, they can visit my channel. I have lot more to give for grade 9 students. I have just started with the audio. I have already recorded a chapter, The Fundamental Unit of Life. You can come to the playlist and check. These days, I'm working on the pronunciation playlist. So whatever you find hard, you can let me know in the comment and then I will come up with a video. There are already few recorded playlists that might help you. Please go and do visit. So we are coming to the title 3.4.1 formula of simple compounds. The simple compounds which are made up of two different elements are called binary compounds. Valencies of some ions are given in table 3.6. You can use these to write formula for compounds. While writing the chemical formula for compounds, we write the constituent elements and their valencies as shown below. Then we must cross over the valencies of the combining atoms. Examples. Formula of hydrogen chloride. So symbol H and Cl for chlorine, and their valencies will be interchanged, means the valency of chlorine will become the valency of hydrogen and vice versa. So similarly, formula of hydrogen chloride has been written as H2S by crisscross method. Can you please write your places from where you are watching this live and share it with your friends, please? Point number three, formula for carbon tetrachloride, it is written as CCl4. For magnesium chloride, we write the symbol cation Mg2 plus first followed by the symbol of anion Cl minus. Then their charges are crisscrossed to get the formula. 4. Formula of magnesium chloride is written as MgCl2, obviously by the crisscross method. Thus, in magnesium chloride, there are two chloride ions Cl minus for each magnesium ion Mg2 plus. The positive and negative charges must balance each other and the overall structure must be neutral. Note that in the formula, the charges on the ions are not indicated. Some more examples. So A, formula of aluminium oxide, which is written as Al2O3 by crisscross method. B, formula of calcium oxide, which is written as CaO. Here the valencies of the two elements are the same. You may arrive at the formula Ca2O2, but we simply write the formula as CaO. Let's come on to the next page, this side. So C is formula of sodium nitrate, which is written as NaNO3, formula of calcium hydroxide as CaOH whole 2. Note that the formula of calcium hydroxide CaOH2 and not CaOH2 means the importance of bracket, because in the second one C only hydrogen has two atoms, but if you write OH in bracket and then write 2, that means two atoms of oxygen and two atoms of hydrogen. We use the brackets when we have two or more of the same ions in the formula. Here, the bracket around OH with the subscript 2 indicates that there are two hydroxyl groups joined to one calcium atom. In other words, there are two atoms, each of oxygen and hydrogen in calcium hydroxide. E. Formula of sodium carbonate. So it is Na2CO3. In the above example, brackets are not needed if there is only one ion present. Formula of ammonium sulfate is NH4 bracket 2 SO4. So in text questions, here we go. Examples are write down the formula of sodium oxide, aluminium chloride, sodium sulfide, magnesium hydroxide. And then question number 2, write down the names of compounds represented by the following formula: Al2SO4 whole 3, CaCl2, K2SO4, KNO3, CaCO3. What is meant by the term chemical formula? And fourth one, how many atoms are present in H2S molecule and PO4 3 minus ion? We come on to the next heading, that is 3.5, molecular mass. In section 3.2.2, we discuss the concept of atomic mass. This concept can be extended to calculate molecular mass. The molecular mass of a substance is the sum of the atomic masses of all the atoms in a molecule of a substance. It is therefore the relative mass of a molecule expressed in atomic mass units or U. Example 3.1a, calculate the relative molecular mass of water, which is H2O. B, calculate the molecular mass of HNO3. Solution. Part A. Atomic mass of hydrogen is 1 U, oxygen is 16 U. So the molecular mass of water, which contains two atoms of hydrogen and one atom of oxygen, will become 2 into 1 plus 1 into 16 is equals to 18 U. Part B. The molecular mass of HNO3 is equals to the atomic mass of H plus atomic mass of N plus 3 into the atomic mass of O. So it will become 1 plus 14 plus 48 is equals to 63 units. 3.5.1, that is formula unit mass. The formula unit mass of a substance is a sum of the atomic masses of all the atoms in a formula unit of a compound. Formula unit mass is calculated in the same manner as we calculate the molecular mass. The only difference is that we come on to the next page. We use the word formula unit for those substances whose constituent particles are ions. For example, sodium chloride, as discussed above, has a formula unit NaCl. Its formula unit mass can be calculated as 1 into 23 plus 1 into 35.5 is equals to 58.5 U. Example 3.2. Calculate the formula unit mass of CaCl2. Solution is atomic mass of calcium plus 2 into atomic mass of chlorine. 40 plus 2 into 35.5 is equals to 40 plus 71 is equals to 111 U. Here we go with the in-text questions that are given here. 1. Calculate the molecular masses of H2O2, Cl2, CO2, CH4, C2H6, C2H4, NH3, CH3OH. Calculate the formula unit masses of ZNO, A2O, K2CO3 given atomic masses of Zn is equals to 65U, Na 23U, K 39U, C 12U, and oxygen 60. So here we go with the summary of atoms and molecules, chapter 3, class 9 science. Point number one, during a chemical reaction, the sum of the masses of the reactants and the products remains unchanged. This is known as the law of conservation of mass. In a pure chemical compound, elements are always present in a fixed proportion by mass. This is known as the law of definite proportions. An atom is the smallest particle of the element that cannot usually exist independently and retain all its chemical properties. Next, a molecule is the smallest particle of an element or a compound capable of independent existence under ordinary conditions. It shows all the properties of the substance. Next, a chemical formula of a compound shows its constituent elements and the number of atoms of each combining element. Next, clusters of atoms that act as an ion are called polyatomic ions. They carry a fixed charge on them. Next, the chemical formula of a molecular compound is determined by the valency of each element. Next, in ionic compounds, the charge on each ion is used to determine the chemical formula of the compound. So these are the exercises that you can read on your own. We are done with the reading of chapter 3, atoms and molecules, class 9 NCRT that is used in the CBSE board. Stay connected to have more such videos. Thank you.